Okay, well, welcome to this supplementary example on finding final velocity using trig. This is example 4 on your handout packet. So what I've started with is listing all the givens. I've sort of taken out the problem. I'm going to leave it to you to read the problem. I think the math is the hardest part, and that's really what we're focusing on here. So read the problem. If you interpret the fact that we've got an initial velocity of 75 kilometers per hour, notice the first thing I did, I started the solution already, is to take that kilometers per hour. Anytime you're working with acceleration, it's good practice to get it into meters per second squared, and that means you have meters per second in the velocities. So standard unit conversion, cancel out kilometers, cancel out hours, take 75 essentially divided by 3.6, and you end up with the same direction, 20.83 meters per second. We're looking for final velocity. We're given a time and we're given an acceleration. So essentially, if you look at the formula, if this was just a one-dimensional problem, you would just sub right into this formula right here and get your answer. Can't do that because we have directions, and you can't just simply add vectors that are in different directions. However, what we can add is we can add vectors using trigonometry or triangles, and that's essentially what we're going to do. I wanted to highlight the fact that what we're adding is a times t, which is a vector times a scalar. Little math tip is that vector times a scalar, you still end up with a vector. Same direction, same units, different magnitude. So let me just show you what I mean by that. A t will be 2.1 meters per second squared of the units directions of 15 degrees. And that would be times 6 seconds. Basically, the units cancel, so I can end up with something in meters per second, which is I want, because I'm going to be adding. I want to add meters per second to meters per second here to meters per second here. I certainly can't add things that have different units. And you end up with AT having a magnitude of 12.6. So AT equals 12.6, ends up being just meters per second, and the direction stays the same. Okay. So now I basically have two things that I can add together. I have my AT, to be my second vector. My first vector will be velocity 1. So let's just look on the next page, and we're going to draw a triangle out of this and solve using trigonometry. Again, here's what we're doing, and really all I'm going to do is draw the triangle. So I'm going to give myself lots of space on this particular one. You'll see why soon enough. My coordinate axis so that I can sketch V1. I want to remind you that if I wanted to do this with a ruler and a protractor, I could actually draw this to scale, and I could end up just measuring V2. Remember, V2 is V1 plus AT. You can actually measure V2, use a protractor to measure the angle and get the correct answer. We don't solve it like that, mostly because I don't have a ruler, and so here we go. Sketching V1 right now. V1, again, is 20.83, 26 degrees west of north. So north 26 degrees west. So like so, and this will be 26 degrees. Okay, and here's my 20.83. Okay, my second vector. My second vector is going to come where this one ends, and it's going to get tight in the corner there to see it because it's south 15 degrees east. So drawing it in here, it's going to be, here's my south, but it's 15 degrees east of that, so it's going to come right over here, and its magnitude is 12.6. So that is tight, and I'm going to blow that up in a second. So my resultant vector then starts at the very beginning, ends at the very end right there, and here's my V2 vector. Okay, so this is an odd-looking triangle, but the point is that it still works. Looking at this corner here, trying to figure out the angles a bit better, I'm going to blow it up here. And what we have right here will represent the 20.83 vector, which is got an angle of 26 degrees from here to here, from here to here. That's going to be 26 degrees. But then I've got my acceleration time vector, which is going to come in here. So I'm not drawing the ends of the vectors, we're just looking at the angles. And in here, right, in that space between the south axis and that vector, you've got 15 degrees. It's south, 15 degrees to the east. So that lets me figure out the magnitude in here, because if this whole bit is 26 degrees, this part is 15 degrees, this must be 11 degrees in sideline. Going back to here, 11 degrees. So let's use cosine law. We have enough information now to use cosine law to solve for V2. V2 squared equals 20.83 squared plus 12.6 squared minus 2, 12.6. Cosine of, it's hard to see on this one, it's an odd looking triangle, but really the angle that's across from my V2, the angle that's directly across from V2 is actually going to be that 11 degree angle. Okay, it's cos of 11, and you can solve for V2, or I'll solve for it, and you can trust me that V2 is equal to approximately 8.8. Okay, so we have our V2, now we need to know the angle. And so probably what I'm going to try to find, knowing that this in here is 26 degrees, if I can find the angle, I'm going to draw a dot to represent that angle dot there, using sine law, then I can add it to the 26 degrees and report V2 as being whatever that is, that sum west of north. So let's go ahead and solve for dot. So if I said sine law, I do sine of dot over across from that dot would be the 12.6. There's the only side not touching it. 12.6 equals V2, which is sine 11, over V2, which was 8.8. And again, you can use your math skills and figure out that the dot angle is 16 degrees, or approximately 16 degrees. Okay, knowing that, I can now report V2 minus V1. V2 minus subtraction here. It actually gives me my answer that V2 equals 8.8 meters per second, 16 plus 26 degrees west. Therefore, V2